Today we are going to be looking at how to plot a quadratic graph. Now I'm hoping this word quadratic is not new to you. Essentially the quad bit just means square. We get that from, if you see in American films, they're always going down to the quad. All they mean by that is they're going down to the square, to the area that's vaguely square shaped. So when we're talking about a quadratic graph, all we mean is a graph where our x is being squared. Okay, so just as a quick reminder of some of the other places we've seen the word quadratic, and we're going to compare it to the places we've seen the word linear. So we first came across the word linear when we were looking at linear expressions. All the way back in primary school you'll have seen these. So linear expressions include 5x minus 4, just b, 3 minus g, minus 7j plus root 2, and 5 lots of p plus 12. So of course the defining feature here is that there is only ever one variable. So in this case x, in this case g, in this case j, there is only ever one variable, and that variable has not been squared or cubed or any kind of power. It is just on its own. So those are our linear expressions. We have also seen quadratic expressions. So quadratic expressions look a bit like this: 5x squared plus 2 minus 6k squared plus 7k minus 2, l plus 2l minus 5l squared, 2z squared minus 2 plus 3z, and f plus 2 lots of 8f minus 3. So of course the defining feature in all of these is that we can have, we don't have to, but we can have a constant term still. We can have a linear term, so as in just 3 lots of our variable, for instance. But we can also now have, in fact we also now have to have these squared terms as well. So x squared term here, there's 2z squared, there's a k squared term over here. Some other things to notice here is that when we're talking about expressions, we're not very fussy about which letter we use, because we know with algebra they can mean any letter. So when we're doing expressions, we do just use whichever letter we feel like. The order doesn't matter. So here we've got 3 minus g, even though normally we'd feel like writing that as minus g plus 3. But the order doesn't technically matter. And over here, yeah, we've got 2z squared to take away 2 plus 3z, whereas we'd normally expect the 3z to be in the middle. The order doesn't really matter. We have standard way of doing it, and the standard way of doing it is this way: the biggest power then going all the way down to the smallest power. Because remember, this is just 2 lots of k to the power of 0, technically. K to the power of 0 being 1. So this is just going down to the lowest power. But we can write it in all sorts of ways. We can also write them in a factorized way. So these two are our factorized versions because they're in brackets. They are still quadratic, they're just written in a different way. Okay, so that's expressions, and I hope we're comfortable with expressions. We've also seen linear sequences. So a linear sequence looks a little like this, and all we mean by that is, well, the first term in my sequence, when n is 1, the first term in my sequence is 1.5. The second term in my sequence is 2.5. The third term in my sequence is 3.5. So we've seen linear sequences, and the defining feature of a linear sequence was that it goes up by the same amount each time, or indeed it goes down by the same amount each time. So here are some more linear sequences. And this one's going up in 3s, this one's going down in 23s, I can see, because that's the coefficient of n. But we have also seen quadratic sequences. So quadratic sequences look a bit like this. We've got an n squared term involved. And again, the order doesn't matter, but we tend to write it in the sensible order. But as long as we've got an n squared term, it's going to be a quadratic sequence. And the defining feature of a quadratic sequence is that the amount it goes up by each time is then a linear sequence. So, for instance, if I looked at n squared plus n plus 2, I would say that, well, x1 is 1 plus 1 plus 2, that's 4. Then the next one is n is 2, so 4 plus 2, that's 6, plus 2 is 8. Then the next one is and n is 3, so that's 9, plus 3, that's 12, that's 14. So you can see the amount it goes up by is increasing by the same amount each time, essentially. So the amount it goes up by is a linear sequence. Now with sequences, we tend to use n. We don't have to. There's no law about it. It's just what we call a preference. It's convention in maths. We tend to use the letter n because we're reminding ourselves that they're integers. That's why we use n, because we're reminding ourselves that these can only be whole numbers. In fact, they can only be positive whole numbers, or occasionally, depending on who you ask, 0. Right, so those are sequences, and they follow the same basic pattern. The linear version has no powers at all. The quadratic version has squared powers. And then finally, we've also seen, very recently, linear equations. And these are the things we've been graphing. So these are all examples of linear equations. It then makes sense, of course, that we are going to have a quadratic counterpart. And that's what we're looking at now, the quadratic equation. So it's a graph that is going to be a bit like these linear graphs, but there will be an x squared term involved. So a quadratic equation, and I'm saying quadratic equation here is in the graph equation, it must have a y term and it must have an x squared term. And just like with expressions and with sequences, we can also have the x term or the constant term, but we can't have anything else. So to put it a little bit more simply, a quadratic graph is normally of the form y equals ax squared plus bx plus c. Now the reason I say normally is because just like with linear graphs, and just like with quadratic sequences and quadratic expressions, we can move this around a little bit. We can change the order, we can change, to an extent, we can change the coefficients because we can times everything by the same amount. We can fiddle around with this a little bit, but this is basically what we're talking about. We've got an x squared term, we've got maybe an x term, and maybe a constant term. So just to show you some examples, on the left-hand side, these are all quadratic equations. So, for instance, y is half x squared plus 5x plus 2 would be a quadratic equation. Y is 2 plus 5x plus a half x squared. See how I've just changed the order around? It's still a quadratic equation, it's fine. Y is a half x squared. So you can see I've just knocked off the 2 and the 5x, that's fine. In fact, I could have just knocked off the 2, so y is half x squared plus 5x. Still a quadratic equation, that's fine. And in this last one, I've just times everything by 2 and moved the order around. So this is still a quadratic equation. This is absolutely fine. So even though it doesn't look the same, it doesn't look like y equals, it's still an equation. Just like with straight line graphs, with linear graphs, we were normally after y equals mx plus c, but we didn't really care if it wasn't. We can still work with it. And on the other side, I've just got a couple of examples of things that are not quadratic equations. So most importantly, this is a linear equation. The x squared term needs to be there for this to be quadratic. And also, we can't just split the variables around, which we could do with linear graphs by coincidence, but we can't do that with quadratic graphs. It has to be the x term that's squared. It can't be the y. This is going to be something slightly different that you will only see if you do A-level further maths. Okay, so here's an example of a quadratic graph that we're going to plot now. In fact, it's the most boring quadratic graph. It's just y equals x squared. So just like we would have done when we started looking at straight line graphs, we are going to start with the coordinates. So we're going to start with a coordinate grid. We're going to work out some of the coordinates that would be on the line y equals x squared. And we do that just by substituting in these values of x. So when x is -3, what's y going to be? Well, y is x squared, so we're going to have -3 squared here, which is 9. Then we've got -2 squared. -2 times -2 is 4. Notice here, now this is really important with quadratic graphs. I'm remembering that two negatives multiplied together are going to give me a positive. So -3 times -3 is 9. -2 times -2 is 4. I need to remember that because otherwise I'm going to make some mistakes when I'm doing my quadratic term, my x squared term. Right, and then we've got -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4, and 3 squared is 9. So that gives us some coordinates that we can then throw into a grid, into a pair of axes. So I can see here, this is the coordinate negative 3, 9. Over here we've got negative 2, 4, negative 1, 1, 0, 0, 1, 1, 2, 4, and 3, 9. Now this is clearly not the kind of graph we're used to. That's because this is a really important point that we need to make sure we understand. A quadratic graph is not going to be a straight line. The reason we call linear equations linear is because they are the equations that will give us straight lines. That's where the word linear comes from. It just comes from line. Quadratics are different. They're going to give us a curve instead. We sometimes still call them a line, but it's not a straight line, it's a curved line. So this is actually what the quadratic graph looks like. And you can see this is essentially a U shape. So about half the quadratic graphs we look at are going to be U-shaped. I'll leave you for a second to speculate on what the other shape is. We will see it shortly. But half the quadratics we look at are going to be U-shaped. There are some things we need to know about this quadratic graph. There are some things we need to be able to label. So the first thing we're going to look at is this point here. This is what we call the minimum point. Now this is an extremely sensibly named thing. The minimum point is the minimum value of the quadratic. So you can see here, there are no coordinates lower than the minimum point. This is the smallest possible point on the graph. And we're referring to the y-axis here, so it's the smallest possible point on the y-axis. So we call this the minimum point. Sensibly named. In this particular example, the minimum point is 0, 0. And at some point halfway through year 10, you will learn how we can get that straight away from the equation, but for now we are just looking at the graph. This red line that I've just drawn on here, this is a line of symmetry. Now that's hopefully not a new term, but it's one that you need to be aware of with quadratic graphs. Quadratic graphs have a line of symmetry. In this particular case, the line of symmetry is x equals 0. So you need to be able to find the line of symmetry. Now these next two terms you'll be very familiar with because we've just done straight line graphs and they are equally true for straight line graphs. So we've got the y-intercept, which is here. It's where it goes through the y-axis, in this case 0. And we've got an x-intercept, which in this case is also 0. Right, so that's the boring one. That's the standard y equals x squared. Let's look at one that's a bit more interesting. Let's look at y equals x squared minus 4x plus 2. Now that's a bit harder to work out from our grid. I'm not going to spend too long on it now, but I hope you remember how to substitute values in, because we need to be able to do that. So I can substitute in these values. So for the first one, it would be negative 3 squared, which is 9. Oh, and then we've got negative 4 times negative 3. So that's actually plus 12. So we've got 9 plus 12, that's 21. Plus 2 is 23. So I would follow that process for all of these. Negative 2 squared is 4, plus 8, plus 2 is 14. Okay, I would follow that for the whole thing, and I would be able to get myself a set of coordinates. If I then plot those coordinates, it looks a little bit different. But that's just because we haven't got a good enough range of values here, because it looks like it's stopping there, but it's not. It is doing the exact same curve thing that the last one did. It's still a U shape. And we can still look at this U shape. We can find the minimum point, which is here. This time is the coordinate 2, negative 2. We can still find the line of symmetry, which in this case is x equals 2. We can still find the y-intercept, which in this case is 2. But oh, here's what's interesting. We appear to have two x-intercepts. It has crossed the x-axis twice. And we can't actually work out exactly what these are. Well, you will be able to by the end of year 10, but for now you can't work out exactly what they are. If you look at the graph for long enough, you'll convince yourselves that it's about 0.6 and about 3.4. So this here is about 0.6 that it's crossing the x-axis. This is about 3.4. So that's interesting. With straight line graphs, we could only have one y-intercept, and one x-intercept. With quadratics, we can only have one y-intercept still. The y-intercept is still pretty boring, but the x-intercept we can actually have two. Far more interesting. Right, so I'm just going to give you one more example. Let's look at the line y equals negative x squared minus 4x plus 2. So the thing I've changed in this one is that I've made this negative instead. This is a negative x squared too. Okay, so I'm going to go through the same process. Well, negative 3 squared is 9, and I'm being really careful with my BIDMAS here because I'm squaring first. I'm doing negative 3 squared is 9. Then I'm finding the negative value of that, so negative 9. Take away 4 lots of negative 3. So that's negative 9 plus 12. That's 3 plus 2 on the end of that gets me to 5. We then got negative 2 squared is 4. So this first bit is negative 4. Take away 4 times negative 2, so that's the same as adding on 8. So that's negative 4 plus 8, that's 4. Plus 2 gets me to 6. And I'm going to do that with all of these very carefully, really making sure that I'm getting my BIDMAS correct, doing everything in the right order. But then when I plot them, I end up with something that looks like this. Well, now clearly this one is slightly different. If I draw on the rest of the graph, I can see that we've now got an upside down U shape. We've got a bit of an N shape. So the key difference between this graph and the last one is that we no longer have a minimum point, because that would be a stupid name. It's no longer the minimum point. It's no longer the smallest point on the y-axis. It's now the maximum point. It is the largest value, which makes perfect sense. It's the top possible value. We can't go any higher than the maximum point. And in this case, the maximum point is negative 2, 2. So if we have a negative x squared coefficient, so this could be negative 2, it could be negative 5, or it could, in this case, just be the negative part. We're going to have an upside down version. We're going to have what I call a frowny face instead. So I always go with frowny face, smiley face. We're going to have a frowny face instead. We still have the line of symmetry, which in this case is x equals negative 2. We still have a y-intercept, which is still y equals 2. And we again have two x-intercepts, still interesting, which are approximately, again not exactly, but approximately negative 4.5 and 0.5. I'm just reading those off the axes. That's pretty much where they go through. That's pretty much negative 4.5. That's pretty much 0.5. We're going to be talking a lot more about x-intercepts in another video. Okay, so the key points from this video. Quadratic graphs are drawn from the equations of the form y equals ax squared plus bx plus c, or something similar to that. Quadratic graphs are curved. They can be U-shaped or N-shaped, or as I say, happy face or sad face. They can have a minimum or a maximum point. They will have a line of symmetry in the form x equals something. They will always have a single y-intercept, always, but then the x-intercepts are more complicated. Because we've now seen an example where we had one x-intercept. We've seen an example where we had two x-intercepts. And what we haven't seen yet, but is possible, is a case where we have no x-intercepts. So there's a lot more to do with this last point.